This will refer back to the parent functions video where we learned about the parent functions. Now we're going to start to move them about. Given a function y equals f of x, the graph of y equals f of x plus c is the exact same graph, just shifted up c units. Now, since you're writing these down, I thought I'd give you a break by saying, listen, if you said plus c, it goes up. Well, guess which direction it goes if you see a minus sign here. That's right, it goes down if it's minus c. So up is for plus. And the graph of y equals f of x minus d. So if at the input station we have x minus d at the input station, in brackets with the x, if we see a minus sign, then that's a shift to the right. The graph of f of x minus d is the exact same graph of y equals f of x. It's just shifted to the right by d units. Guess which direction it shifts if there's a plus sign right in that input station. It shifts to the left. So this is for left, right, and outside on the end is for up, down. Here's an example. Given the graph of y equals f of x, this blue line here, we can see that it's a function. We can see that it passes the vertical line test. Given this, you're asked to graph y equals f of x plus 3. Well, it's fairly simple. First, acknowledge it's shifted up 3 units. So our approach is to take the vertices and shift them up by 3 units. So we'll take this point and shift it up 3. And it's real simple. We'll take this point, shift it up 3. Take this point, shift it up 3. Take this point, shift it up 3. Connect the dots and label your graph, y equals f of x plus 3. An upshift. Let's do another one. Given the graph, happens to be the same graph, sketch the graph of y equals f of x plus 2. So we have to look at this and recognize at the input station, we have x plus 2 in brackets with the x. So that means shift it left 2 units. Notice how it's the opposite way that you would think. I would think that plus 2 would mean go to the right. But no, if it says plus 2, you go to the left. The reason is that what happens at the input station, the action is actually performed on the graph paper. It's the graph paper that shifts to the right too, so the function itself appears to shift to the left by 2 units. With that understood, the action is very simple. Take the corner point and shift it to the left 2. Take the corner point, shift it to the left 2. And again, and again. Join them together, label your graph, y equals f of x plus 2. A left shift. Graph the function, y equals the square root of x plus 3 minus 2. So we have to look at this and recognize the parent function. The parent is y equals root x, because we see this root sign. So it's a root function that's been shifted, but I can see at the input station, which is the radicand, it's been shifted to the left 3. And I can see outside that, it says minus 2, which means down 2. So our solution here is to list the transformations. Shift left by 3 and down by 2. Okay, what? We're going to shift the parent function left 3 and then down by 2. The parent is the root function, so we have to refer back to our knowledge of y equals root x. Y equals root x goes through the origin, and then it goes through 1 over root 1 up. 4 over root of 4 up, and the root of 4 is 2. 9 over and root of 9 up, and the root of 9 is 3. Join them together, and we have the parent function, y equals root x. And to this parent, we intend to shift it left 3 and down 2. So we could take each point and shift it left 3, down 2. Take that point, shift it left 3, down 2. But another approach is to say, this is half of a parabola that opens to the right, and there's its vertex. Why don't we just take the vertex and shift it left 3, down 2? Okay, let's take that approach. That will be our vertex, because it's the original vertex at the origin, shifted left 3, down 2. Now, we've all been children, so we know how to pretend. We're going to pretend that this is the origin. We're not going to look at the actual origin. We shall pretend that this is the origin. And we'll go over 1, up root 1. We'll go over 4, count them, 1, 2, 3, 4, and go up root 4, which is 2. And then we'll go back here and we'll go over 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and up square root of 9, which is 3. Now, the reason I chose to go over 1 and over 4 and over 9 is because I know the square roots of those numbers. Join them together, label your graph. Notice, we're starting to get a little more sophisticated. We can graph this quite accurately and quite simply if we understand. Let's do another one. Graph the function y equals 1 over x minus 2 plus 5. Now, the parent function is y equals 1 over x. We see the 1, we see the x on the bottom of a fraction. We recognize buried in there is y equals 1 over x. That's the parent function. So our approach will be to identify the transformations. And we can see that it shifts right to, because at the input station where the x is, it says x minus 2. So that means shift right to. And then after that it says up 5. Shift right to and up 5. So what we do is we recall the appearance of the parent, which is y equals 1 over x. And we recall that it had asymptotes at the axes. So the first thing we need to do is shift the asymptotes. We have to shift the asymptotes to the right 2 and up 5. So we know that the y-axis was an asymptote, so shifting it to the right 2 is easy. And the x-axis was another asymptote, so we can shift it up 5. And those are our new asymptotes. We shift them right 2 and up 5. We apply the transformation to the asymptotes first. Now, again, we're going to pretend. We're going to pretend that the intersection at the asymptotes is actually the origin. And then just graph y equals 1 over x. If you learn to graph y equals 1 over x from the origin, then you can graph it from this pretend origin. Go over 1, up 1 over 1. Over 2, up 1 over 2. Over 3, up 1 over 3, and so on. Over a half, up 1 over a half, which is 2. Over a third, up 1 over a third, which is 3, and so on. And then the ones on the bottom left, they count 2, so over 1, down 1 over 1. Over 2, down 1 over 2. Over 3, down 1 over 3, and so on. Over a half, down 1 over a half, which is actually down 2. Over a third, down 1 over a third, which is 3, and so on. Join them together, label your graph, and look, you've graphed y equals 1 over x minus 2 plus 5. I'll take these dots off and show you what that graph looks like. It's the blue line with the asymptotes. Find the transformation that maps the first function onto the second function. Take a look at this. Here's a little exercise. If we were 3 units to the left, because we know that at the input station it says x plus 3, so that's 3 to the left, and we want to become 2 units to the right. Let's picture this. There's a reference point. If we're 3 units to the left and we want to move to 2 units to the right, we have to think about it, go from here to here. That's shift right by 5. That's the kind of thinking that a person needs to be able to do. The thinking section, if you will. Let's do a B question. If we were 4 units below a reference point, because this says -4 and it's up, down, and we want to become 10 units below a reference point, think about it, we have to go down by 6. And we can do 2 of them at the same time. If we were 2 to the right of a reference point and 3 above, and we want to go to the actual reference point and then 1 above, let's do the left-right thinking first. If you're 2 to the right and you want to go essentially home, that means shift left 2. And if you're 3 above something and you want to be just 1 above something, you have to go down 2 units. So left 2 and down 2. Let's move on. State the equations of the graphs. Look at the graph. It's a parabola, so the parent function is y equals x squared. But it's been shifted to the right. So for left-right motion, we have to go to the input station, put brackets around the x, and shift to the right. And we've learned that that means put a minus sign at the input station. Shift to the right 3 units, put brackets around the x, and put x minus 3. From our note at the beginning of this video, if there's an x minus d at the input station, it shifts to the right by d units. Take a look at this graph. We see that it's the top half of a parabola that opens to the right. So reference your knowledge of the parent functions. The top half of a parabola that opens to the right is y equals root x. So we've got the beginning. This is the parent, but it's been shifted to the right 4 and up 2. So at the input station, we need it to shift to the right 4. That'll be -4, and then +2. Notice how we're gradually getting more sophisticated, looking at a graph and stating its equation. Let's go again, state the equation of the graph. We notice that it's the bottom half of a parabola that opens to the right. That was one of our parent functions, the negative root x. But this one's been shifted to the left 3. Now shifting to the left, that's going to be at left-right is always at the input station, so right around the x here, we're going to have to do something. First, let's acknowledge shift left 3, up 2. So to make it go to the left, it's a plus sign. So it'll be x plus 3 and then +2. Notice how this minus sign stays put. And there's the equation of the graph. We recognize the parent. The parent is the 1 over x function. But we notice that the asymptote used to be the y-axis. It's been shifted over to y equals -3. It's been shifted to the left 3 units. So the parent function gets shifted to the left 3 units. Not up nor down, because the x-axis is still the horizontal asymptote. So it's just this parent shifted to the left 3 units. At the input station, put an x plus 3. We don't need brackets here because this line functions as a set of brackets, the division line. We recognize the parent, once again, as the negative 1 over x function because of the location of the 2 branches of the function. So there's the parent, y equals -1 over x. Now, the y-axis is the vertical asymptote of this, but the horizontal asymptote is y equals 2. It goes across here like this. So we're going to have to shift up 2. We'll have to take this parent and shift it up 2 units. which means put a plus 2 on the end. And we've identified another one. And finally, I think, we recognize once again the parent function with the top right, bottom left, 1 over x function. And this one's been shifted to the right 5, we can see, and down 4, we can see, because of the asymptotes. There's an asymptote here, and there's an asymptote here. So it used to be at the origin, now it's been shifted to the right 5, down 4. If we can recognize that much, then we understand that at the input station where the x is, we have to go x minus 5, and then on the end, minus 4. How about some grade 9 math? Well, we've got a y equals mx plus b situation. You might be thinking, grade 9? I'm in grade 11. No. The previous grades of math never go away. So this is a line because I could draw it with a ruler. So it's y equals mx plus b. Let's pick a point on it. How about that point? And another point. Well, I like this point because I can see that it's the intersection of a couple of these dotted lines. And from here I can measure my slope. The leftmost point to the rightmost point. We don't rise, but we drop. So dropping is negative rising, and then we run to the right 3. So the slope here is negative 2 over 3. Meanwhile, the y-intercept, here's the y-axis, the y-intercept is the number 4. That would be b. And so we have the equation of the line. Y equals negative 2/3 x plus 4. And a parabola. Looks like a parabola. So it would be our parabola that opens down parent. The parent would be the negative x squared. But it's been shifted down 3, so we simply shift it down 3 with a minus 3 on the end. I'm not really Ziggleby at Beachdoom, but thanks for watching. If you liked it, leave a like or a comment or a question. The comment section would be an excellent spot for a question. And if you like the content, then please subscribe and tell your friends. Thanks a lot. I really do appreciate it.